Okay, this is Introduction to Molarity. You're going to start seeing molarity in the text and reading and some problem sets surrounding it. You might want to pause this at any time and get the core notes this down first and then pick up once you have these things drawn. So useful equations, you have molarity. The definition, it's moles of solute per liter of solution. That's the key thing here. And then we have another useful equation when dealing with molarity is oftentimes we're going to convert between milliliters and liters. We know that there are 1,000 milliliters in 1 liter. So the biggest question to me is, what do these molarities represent? You have one capital M NaCl. And that, unpacking that capital M, that means 1 molar NaCl, which means when we see this, we literally have 1 mole of NaCl in 1 liter of solution, or in enough liquid to make 1 liter of solution. So when we think of moles, okay, we know that a mole, from our past, we know that 1 mole is equal to 6.02 times 10 to the 23rd formula units of the substance we are dealing with. So I'm not going to write out, there's no way I could write out NaCl 6.02 times 10 to the 23rd times. So I'm going to say that every time I write it in my picture, I'm representing 1 mole. Second thing about the NaCl is that it is an ionic salt, which means it dissolves in water. And so when I drop it into the water, I'm going to have 6.02 times 10 to the 23rd Na plus ions and 6.02 times 10 to the 23rd Cl minus ions floating around in my 1 liter of overall solution. So that's literally what molarity means. Okay. In similar setting over here with our glucose molecule. Now, glucose is a little bit different in that it does dissolve in water, but it does not dissolve ionically. So we're still going to have our 1 liter of overall solution. We're still going to have 1 mole of C6H12O6. I wrote out mole this time. I could just go MOL. So 1 mole of that in 1 liter of solution. But now I'm just going to have C6H12O6. So that glucose molecule dissolves in the water, as we know, but it does not break apart in the sense that NaCl does. It's not an ionic dissolver, but the water does dissolve it. Down here we have 2 molar NaCl. Well, what does that mean? Well, that just means that there are 2 moles of NaCl in every 1 liter of overall solution. So if I was going to draw that picture in this case, I've got my solution, and instead of just 1 NaCl and Cl minus ion set, I now have 2 of them dissolved in enough water or enough liquid to once again make 1 liter of solution. Similar idea, but slightly different over here. If I have 2 molar MgOH2, well, what does that mean? That means that there are 2 moles of MgOH2, another ionic dissolver, in every 1 liter of solution. Well, again, I have my 1 liter of solution here. And if I put 1 mole of MgOH2 in there, I get Mg2 plus and 2 OH minuses. That's one piece of that going in because Mg's got that positive 2 charge, and there are 2 OH minuses for every 1 Mg2 positive. Well, we don't have 1 mole of that stuff, we have 2 moles of that stuff. So I'm going to put 1 more MgOH2 in there. This idea will come into play when we discuss colligative properties later on. So there's our 2 moles representation of MgOH2 in 1 liter of overall solution. Notice that 2 moles of the solution gave us 2 moles of Mg2 plus ions and effectively 4 moles of OH minus ions floating around in the solution. Common conversions that you'll encounter in the next several days when dealing with molarity from milliliters to liters. So let's say we were asked to convert, I'll put a number 1 here. Let's say we were asked to convert 375 milliliters into liters. Well, we'd have our 375 milliliters. Put a placeholder of 1 right there. And from up above, I know that there are 1,000 milliliters in 1 liter. So I'm going to put milliliters on the bottom and liters on the top. For every 1 liter, there are 1,000 milliliters. This is going to allow me to cancel out milliliters. I'm going to bring my calculator into play. It's going to show up here or not, but I'm going to go 375. It's not going to show up. Divided by 1,000. I'm going to get 0.375 liters of solution. In similar fashion, we call this problem number 2. If we wanted to convert 4.5 liters and push that into milliliters, we would start with 4.5 liters. Use our placeholder of 1. And then once again, 1 liter is 1,000 milliliters. So our liters are going to cancel. And so we end up with a multiplication problem of 4.5 times 1,000, which is 4,500 milliliters. And if we wanted to go letter of the law with scientific notation and significant digits, we would say 4.5 times 10 to the 1 to 10 to the third milliliters. So it's a little bit of an explanation of molarity and how it can be represented at times, keeping in mind, though, that 1 mole is that Avogadro's number of units. These are just kind of simple representations of that, and some liter to milliliter conversions that you're going to encounter in the coming days as you investigate molarity.